Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by Deepak. In the previous modules, we have introduced the concepts of electric field intensity, electric flux density. From the current module, we see the same parameters, but instead of free space, we will discuss them in a material space. The materials can be characterized into insulators, conductors, and dielectrics. The current module is dedicated to discuss the electric fields in conductor space. Before we discuss any of that, let us revisit the concepts of current. Current is flow of charge. For a given area, it can be quantified as the charge passing through area per unit time. This current is called as convection current. Charge passing through the area per unit time. Thereby, I think you can understand that I is equal to rho q by rho t. If the movement of these charges is because of electric field, then the current is called as conduction current. You may have many of such currents. If the movement of the charge carriers is because of change in charge concentration gradient, then the diffusion takes place, and the movement of charge carriers because of diffusion is called as diffusion current. And sometimes there will be just change in the charge concentration. Such current, it is not current as per se, but it is just that the charge is changing per time because there is change in rho v, which is called as charge concentration. That means a body which has earlier some more charges, for example, say Q, after some time, the charges inside the body have gone down by some small q. After time t. Now earlier the charge were q. Now the charges have gone down. That means the current flowing through the body is minus q by t. What happened to these lost charges? We would see about them. But if this is the scenario that the body has lost some charges, that is, the charges have been displaced. If the charges gets displaced, then such rate of change of charges, rate of change of charge concentration induce the displacement current. We have seen that the current is the number of charges passing through the area per unit time, whereas the current density is the number of charges passing through a unit area in unit time. Current flowing through a unit normal area. Now, if somebody has given you the current flowing through a unit normal area, that can be used to determine the total current passing through an area. The relationship between a density and a parameter is, as we have shown you earlier, is I equals to J bar dot ds. I already told you when I discussed about the electric flux lines. Remember the equation electric flux lines was equals to d bar dot ds bar. At that moment I also told you that this is a universal rule or universal equation for the You may remember by discussing electric flux density, we said that electric flux is the integration of d bar dot ds bar. I also told you that this equation is a generalized expression. It can be generalized to give you a quantity equal to density in the direction of the normal. Density is a density vector here, right? If that is again the same here, the current flowing through an area can be equated as the current density along the direction of normal, which is integrated over the entire surface. This current density can be of three types: the convection current density, the conduction current density, and displacement current density. Convection current density is because the charge is flowing. Conduction current density is if the current is flowing because of the presence of electric field. Displacement current density is current flowing because of the charge concentration gradient. Or no, that would be diffusion current density. Displacement current density would be because of change in the charge concentration. These are the three different current densities. Now let us discuss a convection current. Current is defined as the rate of change in charge. I is del Q by del T. Consider charges flowing with a velocity of u bar inside a body. This is the body, and assume that the charges are moving inside with a velocity of u bar. The cross-sectional area is assumed constant over the entire length of the body. Now, after some time t, del t, let's assume that the body got displaced. The initial point was here, it was the initial point, and after some time del t, let us assume that the body has reached here, whose cross-sectional area is still S, and the displacement it has observed is del L. Okay, the body is moving in this direction with a velocity of u bar. Now, I is del Q by del T. I know that del Q can be written as rho L dl, or this rho S del S, or rho V del V for uniform charge distribution. And let us assume that we have uniform charge distribution, and this can be written as rho V times del V by del T. So the current I have would be rho V times del V by del T. What is V? V is the volume. Del V is the differential volume. Now again, V is S into L. The cross-sectional area times the length would give me the volume, right? The change in volume would be change in the cross-sectional area times length plus change in the length times cross-sectional area. But we have assumed that the cross-sectional area, change in cross-sectional area is 0 because the cross-sectional area was assumed constant, and this product is 0. So del V can be written as S times del L. And the equation for the current would be rho V times the cross-sectional area times del L by del T, where del L is the displacement observed in del T time. So this is nothing but rho V S times u bar, where S is the cross-sectional area. Now, this is the expression I got. I know that the current density is the current flowing through unit surface area. So, I by S is equals to rho V times U bar. So, the current density is, the symbol is Z bar. Z bar is equals to, which is equals to I by S rho V times U bar. This is the relationship between the velocity of charges, charge concentration, and current density. This expression is valid for any type of current density, whether it may be displacement current density, it may be diffusion current density, be it conduction current density. This expression Z bar equals to rho V times U bar is universal. But the type of current density is characterized by what is inducing this U bar. Now, in fact, the displacement current density might need some changes to it, because the charge concentration may also change with time. We'll look at that in later modules, but right now, for our discussion, this is universal. This is called as the convection current density. This is conduction current. Movement of charge carriers due to electric field is the conduction current. It requires mobile charge carriers, free charge carriers. Force experienced by an electron in electric field, we have already seen F bar is the negative sign is to identify that we are discussing for an electron, that is F, we know that F bar equals to Q E bar. Now for an electron, Q equals to minus E. Hence the force experienced by an electron in an electric field is minus E times E bar. Now the force can be called the mass into acceleration, that is nothing but mass times the rate of change of velocity, or the force is the rate of change of momentum, where momentum is mass into velocity. So if we have observed for a time tau, and initially the bodies were at rest, now the bodies are moving with a velocity of m u bar. The bodies are now moving with a velocity of u bar. Initially they were in rest. Now the body is moving with a velocity of u bar. Then the change in momentum is m u bar minus m times 0 by tau. Any way you look at it, even if you consider the expression of mass to acceleration, where acceleration is final velocity minus initial velocity by time, there also you will be getting m into u bar by tau. So this is the force experienced by any body, where the bodies which are start initially at rest are now moving with a velocity of u bar after the observing time of tau. Now these two, which are two different definitions of force, must give you the same quantity. can equate those two, mass times the velocity by tau should be equals to the minus E times electric field intensity, which gives me the value of velocity to be equals to minus E tau by m times electric field intensity. Now, if there are free electrons in a unit volume, that is, if you have a body, inside this body for unit volume, there are n free electrons. The charge concentration is n times E, because one electron would give me minus E charge, and electron would give me minus n E charge, and the charge concentration is defined as charges per unit volume. Hence, I can say that my rho B equals to minus NE. I know that the current density, the charge concentration, and the velocity are related by J bar equals to rho B times V bar. Hence, J bar now is equals to minus NE times minus E tau by M times electric intensity. Now, upon the multiplication, I will be getting N E square by tau times M E. You observe this parameter is directly proportional to number of free charges, is directly proportional to square of the charges, the electron charge, but that is constant, right? I don't have to worry about that. And also another important parameter, tau, where tau is the time observed, where body which was initially at rest has gained a velocity of u bar. This tau is called as relaxation time. This is the time interval between collisions. That is, in a body, when free charges are moving, one electron may collide with another electron. The time gap between two collisions is your relaxation time. This entire expression of n e square by tau times m, m is also a constant mass of electron. Right? This is called the conductivity of a material. Where I already told you that is directly dependent on the number of free charges and the relaxation time. They are material dependent. That is, your conductivity sigma is dependent on the medium, or let us say the material which has been used to induce movement in charge carrier in presence of an electric field. Now, if sigma is equals to 0, that means however high the electric field intensity might be, then J bar would still be equal to 0. That means there would be no current flowing. If sigma equals to infinite, then that means even for high amount of current density, the electric field spin density required is very, very low. Now in this expression, J bar equals to sigma E. Sigma is called the conductivity of the material. J bar equals to sigma E is the Ohm's law. This is Ohm's law, which can be applied universally. From this, I will tell you in subsequent slides that how this has reduced to something which are quite familiar. Let us discuss the classification of materials. In the beginning, I told you that materials can be of many types. The major classification of materials in the respect to electric field are conductors, insulators, dielectrics. What these are, what are the natures of these three different materials, we would see in the current module. All the semiconductors can also be considered as a different class. For discussions of electromagnetic theory, our semiconductors and conductors have no great difference. Hence, we don't discuss them in the current module. The fundamental difference between these materials in presence of electric field are the conductors have bonds inside them which break, and once the bonds break, the free charge carrier. For example, let us consider an atom. Let us assume that there is only one electron in the outermost orbit of this atom. Now, by the definition of ionization potential, it requires some energy for the electron in the outermost orbit to leave its orbital movement and free itself from the attraction towards the nucleus. It is always attracted towards nucleus, but if we give it some energy, it would break out of it and it will come here. Now, because of this has gained a charge. As long as it is inside this orbit, it is bounded by the attractive force towards the nucleus. Once it comes out of its orbit, now it is free to go anywhere. This is called a free charge carrier. Now, in presence of an electric field, for example, a positive and negative, this will move towards this positive, given that it has enough strength to pull this out of its bond. Right? Now, the conductors require very small amount of such force. Thereby, they are prone to give us free charge carriers. Hence, the name are conductors because it allows the current to be conducted. The meaning of allowing current to conduct is it supports the flow of free charge. Insulators, they are generally formed by atoms which are involved in strong covalent bonds. And impractical strength of electric field are required to break these bonds. Hence, there are no free charge carriers inside. Generally, for example, again, let us consider a nuclei, an inner orbit, and an outer orbit, and assume that it has 7 free electrons inside them. Now, you know the nature of these atoms is to get the configuration of NS2 and P6, the most stable configuration. Right? Now, it already has 7 electrons inside them. And that means these 7 electrons are strongly attracted by 7 positive charges at the center. Now, the ionization potential required by these type of atoms would be very, very, very high. Yes, theoretically, you may cause these electrons to come out of it, but it requires impractical sense of electric field. Thereby, the electrons are always attracted towards the nucleus. And they would not be coming out of this orbit giving free charge carriers. There would be no free charge carriers. These are insulated. Thereby opposing, because there are no charge carriers, they cannot support the flow of current. Hence the word opposing, but what I mean by opposing means they cannot support the flow of current to it. Dielectrics. The dielectrics are a special form of materials. They also won't give you free charge carriers, but they do react to the electric field. The molecules inside them, for example, let me discuss this atomically, because atomically it would be very easy for me to show instead of showing them at a molecular level. Understand that I am using atomic level representation to illustrate the points of molecules. Right now, imagine that you have a nuclei, you have an inner orbit, and you have an outer orbit. Okay. Now, an electric field is such that the positives are attracted this way. That means negatives are repelled this way. Now, because of this electric field, the electrons inside them are still bound to the nuclei. They are not coming out of it. But what they do is, instead of this symmetrical structure, they form, they won't orbit exactly around this path, but they stretch their radius. Okay. Now, this is how the atoms of the molecules, the basic molecules, the fundamental molecules inside the electric react. This stretching of this atom or molecule is called as polarization. What would happen because of this? We would discuss in detail in the next module. But right now, let us discuss how a conductor reacts in an electric field if it is kept isolated. Conductors have free charge carriers. They are electrons, as we know. Electrons move in the direction opposite to that of electric field. We also know that because electric field points towards the motion of unit positive charge. Electrons have opposite charge, but hence the electrons move in the opposite direction as that of electric field. Imagine that you have a conductor over here, and this is the direction of electric field. There is an electric field, and a conductor is placed inside an electric field. Right? Now all the positives would be going this way, all the electrons would be going this way, and all the positive charges should move this way. Right? That is the definition of electric field intensity. Now I have a charge conductor here. This is the electric field intensity I have, and all the positive charges gets deposited. The positive charges, in the meaning of positive charges is once an electron break out of it, then this becomes a positive ion and this becomes a free charge carrier, right? Similarly, what I meant by a molecule is, if, for example, if I have NaCl, once the bonds break, Na plus would be a positive ion and Cl minus would be a negative ion. Cl minus, all Cl minuses would be deposited here, and all Na pluses would be deposited here. Right? Again, let me tell you that NaCl is an example to illustrate an ionic bond. Right? I'm not saying that NaCl is a conductor. Of course, NaCl do conduct electricity. To test that, you may use a small experiments with adding NaCl in the water and testing its conductivity. Now, the charges accumulated inside there are now at rest because these charges which are accumulated on the surface can't move. They can't escape this body. They are stuck on the surface of the conductor. Hence, these charges at rest create an electric field. This magnitude of the internal electric field is same as the magnitude of the external field, that is this A bar, E bar. This is E bar external, which has been applied, and this is the magnitude, the electric field because of these charges is E bar induced. Right? This is the induced electric field. These two are equal in magnitude, but the directions are opposite because the external electric field induces positive charge to move this way, whereas the internal electric field induces the positive charge to move that way. Thereby, the net electric field inside the conductor is from the relation between E and V, where V or E always points towards the decrease in V. When E bar is 0, that means V is also 0. Hence, the conductors are also called equipotential. Right? I hope this is pretty clear. Now, what would happen when a conductor is supplied with a constant potential difference across it? Let us assume a conductor with a cross-sectional area S and its length be L, and it is connected to a battery with a potential difference of V. Now, you know, because of this, the current will be moving from right to left because current outside the battery, the electrons move towards the positive terminal. Because the electrons move towards the positive terminal, the current moves in the direction opposite to it. Right? And because of this constant potential difference, a uniform electric field would be created, where the relationship between the electric field and the potential is E equals to V by. Because of the constant cross-sectional area, the current density is J equals to I by S. We have already established that J equals to sigma E. Using that expression, I can say I by S equals to sigma times V by L. So V equals to L by S sigma I. Let us rename 1 by sigma inverse of conductivity by rho, and let us call it resistivity. Then V equals to rho L by S. This is V equals to Ri. This is something which we have been studying from our childhood as Ohm's law, but this is applicable only when a conductor is supplied with a uniform potential difference, constant potential difference, and the entire cross-sectional area of the body is constant. Only in such scenario we can apply V equals to IR to get the expression of voltage cell. This is the Ohm's law, modified Ohm's law, whereas the universal Ohm's law is J equals to sigma. Now the resistance can also be written as V by I, right? But this V by I is applicable only for the given conditions. Let us try if this expression can be used to get an equation for resistance which can be used for any distribution. For non-constant electric field intensities, the relationship between the potential difference and the electric field intensities can be characterized as E bar dot dl. I have removed the negative side for obvious reasons that the resistance can't be negative, and current for non-constant cross-sectional area is J bar dot ds. Now if I substitute them, I will be getting R equals to E bar dot dl by sigma times E bar dot ds. This expression can be used for any scenario, and this would still give me the resistance of the material, or resistance of the conductor in question. Now let us consider a conductor whose current density, conduction current density J bar, is in this direction. Now the current, if we assume a closed surface, then the current flowing out of this closed surface can be obtained by closed surface integral of J bar dot ds. But I know that the current flow outward would be equal to the rate of change in the current inside the body. But I know that the current flowing outward is equal to the decrease in charges inside the body. That is, only if the charges inside the body decrease, only then the current can be flowing out. If I equate them, I apply divergence theorem again to convert the closed surface area to a volume integral of the divergence of J. Again, this also can be written in terms of its charge concentration, rho b. So, upon comparison, I can write and come to a conclusion that the divergence of the current density is the rate of change in the charge concentration. This is called continuity equation. This equation would be having a very important role in the later module. But right now, this is the continuity equation and this is the discussion stop. The reference of the topics which we have discussed, please follow Elements of Mathematics by